All right, welcome to Computer Science 305. This is object orientation, and so we're going to go through a few things today. The main concept, first off, is that we need to ask ourselves if we can figure out what are the definitions for an object-oriented language and object-oriented programming. And we have to ask ourselves if even if we can come up with what we might call a definition for these, will actually matter, and given the nature of technology, the nature of computer programming. And so these are just things we need to keep in mind as you're listening to this and we move through. We do have a couple of observations of note, right? First off, object-oriented programming is not the same as programming in object-oriented language, right? And furthermore, not all object-oriented languages are like Java. Two things we have to know. We know the second one from our experience with Ruby, even though we weren't programming in an object-oriented way, but most people noticed a significant object-oriented issue with that. Furthermore, if you use Python in an object-oriented way, you definitely know that it's quite different, or seriously different from programming in Java. So the outline for today, basically there's two major things we're going to be talking about: object-oriented programming, object-oriented language features. And this first part of this lecture will cover the object-oriented programming. And so we have two main things we're talking about there: OO in ML and non-OO in Java. And I'm going to kind of breeze through the ML part. It's more of an example. We're not going to be writing any code here. So let's think back to the last lecture in Java, and we were creating the node class, and actually it's both I believe it was in both the actual Java lectures. We created the node class, and essentially node, as we see here, is just really simple. We have a constructor, we have two pieces of data, we have the actual data that we're holding and the link to the next node, and then we have the two getters, get data and get link, right? We use this to build a stack of strings. So we have the node class, as I just mentioned, two fields, one constructor, two methods. And if we were to think about these methods in their most abstract form, they're really just a message that we send, right? We say to a node, what is your data? What is your link? Right? And it responds to us with something like a string or another object. So essentially, we can think of any type of method call on an object as a message that we're passing to it, and we're getting back something of a response. And so that's this message to response data type that we see at the bottom here in the ML parlance. So if we were to think about this, we could redefine and create a concept that's almost object-oriented in ML. If we were to create a message data type and a response data type, we could then create a function called node, which is like a constructor that takes in a data and a link and get data, or a node, data, link, and get link, right, for the other side, and then returning data or object. And essentially, right, this would do everything we want. It always results in a function type. Result is a function of type message to response. And essentially, it's going to construct a more object-oriented way of thinking about ML. And then we can implement it. We can actually run it and see that we get something like this, right? Essentially, what we're getting out of this is that we have objects responding to messages. We do need to eventually define null to be something, right? We could essentially create the function null, which takes in any value and returns null as a response, right? A string value of null. That'd be fine. And furthermore, we could utilize this to create the stack class by including the top field and then three more methods: has, more, add, and remove. And we can implement it using a linked list of node objects, right? Well, that's all great. Should be good. Except for it starts looking like this, right? Now we have message has been greatly expanded. We have response has also been expanded. And then we had to define another function that takes in anything called root. And, what we start seeing here is that it's not quite what we're looking for in an object-oriented system. It would give us the capability to program object-oriented, for example, as we see here. We've started to create all the things we need. We have null, which gives us the capability to create is null, or just a null message, right? We also have this capability to construct our nodes, construct our stacks. Everything we need is there. The problem here is, and if we see here, it returns almost exactly what we expected from the same results we would get when we implemented this in Java. But now we're doing it in ML. And it looks, well, it doesn't look too bad. It looks more annoying than anything else, but it gives us the capability to do basically everything we want to. Except for, it's not really going to give us what we'd normally think of for inheritance, right? What we had for inheritance was, from our stack class, we could implement peekable stack, which just gave us the capability to ask, to say peek, and it would return the value of the node pointing to by top. And what we get here is, if we take a look at this, we get the exact same thing, right? We have peekable stack. It's a constructor for peekable stack, and then we give it the top and the peek, and it returns top get data. So seems to work. Seems to look good, but this is a little less of what we were looking for. This is more akin to Smalltalk style. It has very, very much, it's a message passing system, right? We have the item that we're passing the message to, but we lose certain things, right? In ML is really well known because it's a strongly typed language. It only needs a little bit of information to figure everything out. Except for here, we have message and we have response as our two data types, and unfortunately, that's as deep as we can go. We cannot statically type beyond that, and which is a problem, right? So our messages are not statically typed, and furthermore, but we do get the capability for the superclass to handle unhandled messages, right? So if we have like peekable stack, anything there that's will be handled by the stack class or stack type that we created. Will handle any other methods that are not what we'll call peekable stack methods. So it does have some of that going on. But the problem is if we go back and look at this, right, we start looking at this stuff, this is not quite what we normally would expect to see from, for example, ML, right? These are not necessarily like, it's not functionally defined things. This is kind of, it's really kind of dirty looking ML, basically. And so, and furthermore, as I just mentioned, messages and responses are not properly typed. We lose our capability for compile time checking for whether or not a given object can actually handle a message. So we don't have the usual benefits of ML, nor do we have the benefits, the full benefits of what we normally consider to be a part of object-oriented programming. In essence, we've kind of broken the concepts, both the typical things that we normally see in ML. And so if we really do want good object-oriented in ML, then we get to things like OCaml or Objective Camel or F#. But the only thing we had to realize here was that, yes, it is possible that we can do object-oriented programming in ML, but that this is confirmation that object-oriented programming is definitely not the same as having an object-oriented language or programming in an object-oriented language, because the system was not built for it. Furthermore, we also can do non-object-oriented programming in object-oriented language systems. So, for example, we know that in Java, it's better to use Java than ML for supporting object-oriented style programming. I would even make this argument for Python, Ruby, and C#, just off the top of my head. And C++, right? All known object-oriented systems that can handle object-oriented style better than ML, right? But in all of those languages, there's no guarantee that you're going to be doing things in an object-oriented way. For example, in Ruby, I made you guys violate all of the object-oriented principles and do things in a procedural way. Same with C++. You can just do everything in procedurally. In Java, you can do everything procedurally. In Python, you can do everything procedurally. But in Java, as we're talking about specifically, we can do that by having essentially one class that has a main method, and in that main method we have just everything, and main must be static in order to be executed, right? So if we just have a bunch of static methods inside of our class, and then we put all that code in just one large class, now what we're doing is, one, we're trying to do global things inside of an object-oriented system. That's an anti-pattern in itself. A pattern of doing things poorly is an anti-pattern. Putting all the code in one big class is another anti-pattern. It's called the God class. It's a bad way of doing things. Furthermore, when we tend to do this, we start forming small classes of just data, right? They have typically public fields and no methods. These are which are like structs in C. These are essentially what we call data classes or data holders. They're effectively useless, and they usually are only used by a God class or a brain class or a schizophrenic class, depending on who you talk to. And so this itself is what we call code smell. It's something that tells us that we need to fix our code. So we'll see this using classes records, right? If we were to do the stack and node concept with just data holders, we basically have a node that has just the data field and the link field, and a stack that has only the top field. And then we would put all the methods, all the stuff that uses this data, we move that into its one main large class, right? Similar to this. That all these would be static, right? So we'd have some stack. So we'd have a method. All the methods take in a stack, and then they operate on that stack. Outside of it, right? The whole point of object-oriented is that we have the behavior, the methods, and the data together and encapsulated in a single structure, right? That way we can instantiate it multiple times as we need. And we also, in an object-oriented system, kind of never want to have public fields, and because we want to have some sort of control on who can manipulate this data and how it's manipulated. That's the whole point of having methods in those classes operating on that data. It gives us a way to ensure safety of the data as well as many other things, and also makes it more maintainable. Furthermore, polymorphism is a concept, right, from object-oriented systems. So normally, if we were to think about this, if we go back to the second Java lecture, we talked about using interfaces, using extensions of classes, right? And we looked at how we can make a work list, and we can implement that using the stack and the queue. And the whole concept is that we would inherit the interface defined by work list in our stack and our queue. And that was, I think it was like 2 methods. I don't remember what they were, but regardless, we can escape this by just having work list, and then we can have special control variables that tell us the type, and we'll see what this is. This is a bad way of doing it. Non-object oriented in an object-oriented system always leads to poor ways of writing code. Don't do these. So if we were to do this in work list, right, what we'd end up doing is we'd have to create a stack, a queue, and a priority queue, constants, which are then used in this variable type, right? And essentially, go back, type then tells us, and furthermore, we would have extra fields, right, that are specific to each one of those given types. So it's basically like we took all the implementations and we're going to put them together into one class. And the control of when to use those different implementations or different code related to those implementations is dependent on this field type. What this really tells us is if we ever start doing something like this, we need to rethink our design, our implementation, because it's bad. So now so this leads us to, for every single one of these methods, for example, add, remove, is empty, we would essentially have the same pattern where we check, is the type equal to stack? Is the type equal to queue? Is the type equal to priority queue? And even worse is, in the way that we're doing it here, we have this nasty, we made add and remove statics. So this is essentially the worst possible way of implementing an object-oriented work list in Java. This is like the worst way of doing it. But this specific implementation, the way it's doing here, anytime we do this type of, if you're doing an instance of check in an if structure or a switch, or if you're doing this would actually be better implemented as a switch on type, like switch W type, and then each case would be work list stack, work list queue, work list priority queue, etc. Doing that is called the switch statement or ifs code smell. It's nasty. Don't do it. If you do start doing something like this, you may need to rethink your implementation. Just bear that in mind. So the drawbacks to all this is you're writing the same repeating branching code, right? So the problem here is not only are you constantly repeating yourself, but furthermore, having this code creates essentially potential for having a significant number of errors, right? It also violates what's called the open-close principle, right? Open for extension, close for modification. Every single time you need to add a new type, you have to go in and change every one of these branches. You may forget that. This is also because you may have multiple methods with the same type of branching construct. This then becomes a form of what I would like to call shotgun surgery. It's another type of code smell. This is all bad, right? So, and then depending on the language, there may be no way to avoid wasting space if different kind of records are required for different fields, right? Space in memory, space in a database. If you have a database records that are this stuff is being persisted to. And then obviously there's all sorts of maintenance tasks associated with this, like adding a new kind of record, removing a previous kind that you don't need anymore. Furthermore, it can cause issues with other code that is based on this. So you have to be very concerned when you start dealing with this. It's better to refactor this into multiple classes if you ever see this in your code. The advantages that we have from OO, though, are that we know we can define interfaces. Interfaces guarantee certain methods are available for any class that implements them. We know that the language system will automatically dispatch to the right implementation for an object. Different implementations of interface do not have to share fields, so that means that we have data encapsulation capabilities. And furthermore, adding a new class that implements interface is easy, right? Because we're following the open-close principle. It's always easy to extend and implement new things rather than having to go back in and constantly change stuff. And also prevents us from, when you start modifying existing code, you start causing errors to occur. So what this all comes down to is that essentially we've learned that OO programming is not the same as programming in an OO language, right? You can do it in a non-OO language like we saw with ML, but it's probably not a good thing to do, mainly because we're not going with the flow of that language. And we can also avoid using OO in an actual OO language, which also should be avoided because now we're violating the flow of that language. And so just go with the flow and enjoy it. Typically, though, in an object-oriented language and an object-oriented programming style, they kind of go together, right? Because that makes sense. But when you kind of violate this, what I keep calling the flow of the language, like the way it works, the language system and how it was designed, you start getting just overall poorly designed code. It doesn't mesh well. In Ruby, we call it Ruby-esque programming. When you go with the way that it's intended and how it was designed. In Java, we normally see this, right? You have certain things that we expect, like if you want to know the value of a field, you call get. If you want to change the value of a field, you call set. All these different things. We know that this is what was intended by the designers. If we go with that, it tends to work better, it tends to look better, and it tends to avoid maintenance issues later on. So that's kind of the end of this first section. Upcoming, we'll talk about language features. So I'll leave that to the second part.